PQ will essentially give me a normal with respect to the source according to the equation. Right? So this is the intersecting point on my image plane. It's always going to be minus P minus Q1 divided by the parameter. Square root of P squared is Q squared plus 1. So I have an easy way of computing my normal under this geometry. Okay. So this actually is called the gradient space. Okay. And the realization of this really comes from the notions of isochords, where if I look at these reflectance maps as gradient maps, how does the reflectance from a particular local patch spread on my imaging plane? And these things will actually spread as isochords. So you will see these contour maps, if you will, in the gradient space, and the contour map will maximize itself where you have the source point and the projection point actually making the maximum value based on the normal that I can. So the true normal for any surface is the one where the contour is maximized, it's concentrated. Everywhere else, if you go, the contour is going to spread out. The further you go from there, basically you extend out to something which you just have a flat line in the gradient space. So this was actually something that was observed back in '86 by Horn. Right? So he looked at this when he was trying to solve the problem of reconstructing the surface geometry based on multiple images. So this is actually what people use in order to find the true geometry at any given surface. Of course, if you simply solve this, I get one estimate, right? For a single source of light, I get one estimate. But if I solve the same point for multiple light sources, what you get is the intersection of these isochords. And if you start getting the intersections of the isochords, that's where you find your optimal point, optimal normal. Right? Because for every light source, I'm going to get a normal calculation. And the normal that is true at any given surface is actually the maximum that you get across all light sources. So then our image model actually becomes quite simplified. Right? So the way we actually go about solving this is that I have some known source vectors, right? Because I have multiple sources of light. It's a vector, S sub j. And for each one of them, I will have a corresponding set of intensity values, I sub j, at position x comma y. We also assume that the response function of the camera is linear, right? So let's just say that my intensity is some scale factor. So I'm going to combine the unknown normals, which is n of x, y, right? So for the underlying surface, the surface is constant. The surface doesn't change. So the normal across all my x, y's is the same, right? Independent of the number of images I capture. So it's just n of x, y. And the albedo is the same, right? So the rho of x, y. I'm going to combine those constants into one value, right? So into one vector. Just call it g. And then, of course, the scaling vectors and the source vectors also we can combine into another vector. We call it v sub j, which is now a vector dependent on the image. So the relationship that I get is, under the immersion model, is that intensity for a given image is constant multiplying by the radiosity. So, which now I'll express further as constant times the albedo, and the normal times the S sub j, the source vector for the jth image. And then, of course, this is rho times n, so I'm grouping the things that are independent of the number of images I have, and the things that are dependent on the individual image value. And then, so this becomes one vector and this becomes another vector. Okay? So, this now becomes a p-square problem. So, on one side I have all my intensity values, so n by one known source, known value. I have the b vector, which is n by 3, right, which is also known. Right? I know my source, and my constant is some constant. And then you're solving for the unknown, which is a 3 by 1. Right? So, we've constrained this problem, simplified it, and converted it to a least square solution to getting G. Now, once we get G, we can get G out of this, right? Once I get G, basically, I know that N, G is actually a combination of two vectors, N and the albedo. But N is a unit normal, right? And the albedo, so that should be rho. Albedo is nothing but the magnitude of G, right? So finally, I end up with saying that N is nothing but G divided by albedo. Okay, so an example of this would be something which will look like this. So I end up having a surface, right? You can see something at this point which is probably this planar, or shapes. I'm moving my light source around, I end up with 5 images. I can solve this least square problem. I can recover my albedo. And if you look, this is what the surface map looks like. This is nothing but the normal map. Right? So this is normals being plotted with respect to the points or pixel positions on that particular thing. And what you see is actually it's more of a dome type structure. So under this constraint, photometric stereo, we can actually recover the geometry of the surface. Quite nice.
Why do we see N light sources? Why not only see?
Why not what?
Only see light sources.
Sure. I mean, you can very easily do that, right? I mean, in general, so you can now step back and say, well, how many light sources do I really need? What are you solving for, right? You're solving for it's a least square problem. So you're solving some certain number of unknowns. So if you know the number of unknowns you have to solve for, you basically have to constrain it by a certain set of equations. So how many unknowns do we have? Okay. So yeah, I mean, I really only need 3, right? But having more will the least square problem, right? So the least square solution that you're getting. So having more will increase your chances of getting you a better solution. So you can have more, but you don't need a lot more. Okay. Yes. No. The membership simply means that the amount of light reflected is uniform in all directions, independent of the direction of the source. So all that means is albedo is constant. So your albedo is just albedo of x, y, as opposed to now something that's directional. Okay. Now, so we said that we can, we have to get the normals, right? I mean, in general, we do all of this so we can recover the geometry. So albedo is one thing, right? For a Lambertian surface, albedo becomes easy to get out, but we have to get their normals. So the normals in general is also relatively easy to get back. Keep in mind the normal in general is of this particular form. We looked at this when we looked at the local information. So we said the normal is nothing but minus q1 divided by the magnitude. So it's basically of this form. We know the vector that we actually solved for g. Is basically that vector. So all we have to do is, in order to compute the components that we need in order to grab the normal, is we can compute the x value. F sub x is nothing but g1 by g3, and f sub y is going to be g2 by g3. So I can compute those very easily, plug it back, and at every point I end up with a normal value. Right? So that's a relatively easy way of recovering.